Hello, in this video I will introduce you about circular motion and its applications in real life. So first of all, what is circular motion? Well, if you look around yourself, the fans, a roller coaster, and believe it or not, the Earth's motion is also in circular motion. The Greek scientist Aristotle considered circular motion as a perfect and natural motion. But is it? In a uniform circular motion, the speed of an object is constant, but then another great scientist called Newton came in and said, but it's actually accelerating according to my theories. Newton's first law states that an object will stay rest or continue in a straight line unless acted upon by a force. Recall that velocity is a vector unit and it has directions. In circular motion, orbital velocity is the instantaneous direction and speed of an object along its path. For circular motion, its magnitude is constant and inversely proportional to the period of the orbit. Notice in a circular motion, the directions of the object moving is always changing. Thereby, the velocity is never constant. So there must be a force acting on the object so as to keep it moving in a circular path. For example, when you're swinging a rock, you must have a rope attaching to the rock. And when you start swinging it, you're actually providing a force to the rock. Also, you can notice that for any moment in the motion, the direction of the force is always towards yourself, or in other words, the center of the motion. Therefore, this force is named centripetal force. This centripetal force will then provide a centripetal acceleration, which is why the object keeps changing its direction. Another observation we can make is that the velocity at any moment is a tangent to the circle, which is quite obvious because, once again, imagine you are swinging a rock with a string. When you let go of the string, the rock will not continue moving in a circle, it just flies away as a tangent. There are three important equations for circular motion. The first one is that the centripetal force acting on an object is equivalent to its mass times the square of its velocity all over the radius of its circular path. When we apply Newton's second law, as it states, force equals to the mass of an object times its acceleration. When we simply rearrange this equation, we get acceleration equals force divided by mass. But the force acting on this object is already defined, that F equals mv squared over r. So when we sub this value into Newton's second law, we can simply get that acceleration equals velocity square divided by the radius, which is very useful when dealing with questions about circular motions. The third equation is Kepler's third law. This equation can only be applied in space where objects are orbiting around a planet or a star. It states that the cubic of the radius divided by the square of the period equals to the universal gravitational constant times the mass of the planet in the center divided by 4 pi square. Interestingly, we can notice that the mass of the object performing the circular motion is irrelevant in this equation. Let's see how this equation is derived. First, the centripetal force is calculated by universal gravitational constant times the mass of the object times the mass of the planet. This thing divided by the square of the distance between them, which is the radius of the circular path. But as we know, the centripetal force is also mv squared over r. So we can equate them together and make velocity the subject. So we can derive that velocity equals to the square root of gm over r, where m stands for the mass of the planet. However, by definition, velocity is distance divided by time. In circular motion, the distance traveled is the circumference of the circle, that is 2 pi r. and the time takes is the period t. So once again, we can equate these two equations together. By squaring both sides and rearrange, we can get Kepler's third law equation. Furthermore, the only variable at the right-hand side of the equation is the mass of the planet. Therefore, any object orbiting around the same planet will satisfy this equation. Next, we're going to investigate the relationship between velocity and centripetal force. In this investigation, the independent variable is velocity, and the dependent variable is the centripetal force acting on the object. There are two control variables. One is the mass of the object, and the other one is the radius of the circular path. In order to investigate this relationship, we have to use this simulation. At the center of the screen, we can see a blue point. That is the object that we are going to spin, and it is going to orbit around the crosshair. At the left-hand side, we can see there are a few variables that we can change, including the speed, the radius, and the mass of this blue object. Before we start the experiment, let's first verify our observations. When we click the acceleration button, the red arrow representing the acceleration is always pointed towards the center of its motion, as we can see. And similarly, when we click the velocity button, we can see that this green arrow is always a tangent towards the circular path. So let's begin. First, we should make sure that the radius is set to 20 meters and the mass of this object is set to 10 kilograms. These are our control variables. And we were going to change the speed to 10, 15, 20, 12, 25, and 30. As we can see, when the speed increases, the net force also increases. So, when we collect all the data, we can plot all this data into log_pro, and a parabola appears, as we can see. This shows that the net force increases exponentially as the velocity increases. But when we plot the square of the velocity into the graph, a linear relationship is shown. Therefore, the centripetal force is proportional to the square of the velocity. This verifies the equation F equals mv squared over r. Furthermore, since the mass is 10 and the radius 20, the constant of this equation is 0.5. And we can easily see that the gradient of this graph is also 0.5, which further verify this equation. A special case of circular motion is when it spins at an angle to the center of the motion. As you can see in the diagram, the tension force from the string divided into two components, and they can be calculated by using a little bit of trigonometry. The vertical part of the force is tension force times sine theta, where theta is the angle made by the string and the horizon. This force cancels out with the weight of the object. Therefore, the net force in vertical is 0. In horizontal, however, the force applying to the object is F times cos theta, and it provides the centripetal force just as in normal cases. So, why is it necessary to understand circular motion? Well, by understanding it, it allows us to develop things like satellites. By controlling the velocity and altitude of satellites, it is possible to keep it in an orbit around the Earth, or even remain at the same position above Earth. You can imagine it as an invisible man using an invisible string providing an invisible force to a satellite. That imaginary force is the gravitational attraction force applied by the Earth. There are mainly two types of orbits. The first one is low Earth orbit. It is an orbit higher than 250 km but lower than 1000 km. The velocity required for the satellite is 28 km per hour, and it takes 90 minutes to travel one complete circle. The other one is geostationary orbit. it has an altitude so that its period precisely matches the Earth. This corresponds to an altitude of approximately 36,000 km. In this type of orbit, the satellite is able to maintain at an exact position above Earth, which is extremely useful in applications such as GPS. Those altitudes and velocities are calculated by Kepler's third law as mentioned previously. Another issue associated with circular motion is orbital decay. That is, when an object is constantly decelerating, its distance to the center of the motion, or altitude, will decrease as its velocity is not enough to keep it moving in the original orbit, and it will eventually reach the center of the motion or stop by the Earth. By applying orbital decay, it is possible for spacecraft to safely re-enter the Earth, because the atmosphere contains lots of air particles and is able to slow down spacecraft. However, the angle which the spacecraft enters the atmosphere should be between 6.2 to 7.2 degrees, because if it is too shallow, the spaceship might skip off the atmosphere because the deceleration provided by the atmosphere is not enough to decay the orbit, so it will just continue in its orbit around Earth. However, if the angle is too deep, the friction between the spacecraft and the atmosphere converts a huge amount of kinetic energy and potential energy because altitude decreases. Those two types of energy are converted into the form of light and heat. The heat generated will collect to a dangerous amount and eventually burns the craft. Also, this sharp decrease in kinetic energy also causes a large deceleration, which results in a huge G-force experienced by the astronauts. G-force is the force experienced by an object comparing to its normal weight. It can be calculated by the formula G-force equals G plus A all over G, where G is gravitational acceleration and it's 9.8 meters per second square, and A is the acceleration of the object directing upwards. If this G-force is too large, it will threaten the safety of the astronauts. Therefore, an angle between 6.2 and 7.2 degrees are recommended. Also, astronauts should be seated facing upwards such that the G-force they experience is minimized. Another issue associated with safety entry is ionization blackout. Ionization blackout is a period of no communication with a spacecraft due to a surrounding layer of ionized atoms. This layer of ions is formed by the extreme amount of heat generated during re-entry. Lots of kinetic energy are converted into thermal energy. This layer of ionized atoms reflect all electromagnetic signals from the spacecraft. Therefore, the communication is cut off. Welcome back to Earth, and let's do a few HSC past questions to revise what we have learned today. This is a question from HSC 2006. It says, two satellites, X and Y, are in circular orbits around Earth. Their masses are identical, and their orbital radii are r and 16r respectively. And we are asked to find the ratio of their orbital periods, Tx and Ty. The first thing we can realize is that there are two things orbit around the same object, Earth. So the first formula we can think of is Kepler's third law. So in this question, we can notice that radius x cubed divided by tx squared is equal to ry cubed divided by ty squared. So from the question, we know that Rx is equal to R and Ry is equal to 16R. So let's substitute those values into the equation. We get R cubed divided by Tx squared equals 16R cubed divided by Ty squared. So obviously we can cancel out those r cubed very easily. And when we do that and rearrange the equation, we get tx squared divided by ty squared equals to 1 over 16. So let's square root both sides and we get tx divided by ty equals 1 on 4, which gives us the answer, which is A, 1 to 4. Second question. In July 1969, the Apollo 11 command module are orbiting around the moon. The mass of the command module was 9.98 times 10 to the power of 3 kg, and its period was 119 minutes, and the radius of its orbit from the moon's center was 1.85 times 10 to the power of 6 meters. In part A of the question, we are asked to find the mass of the moon. So once again, we need to use Kepler's third law. And we can notice from the question, the radius, the period, is given. So we can go ahead and sub in those two values. So we can get to the second line here. And by rearrange and make m, which is the mass of the moon, the subject, we can get that the mass of the moon is 7.35 times 10 to the power of 22. In part 2 of the question, we are asked to find the magnitude of the orbital velocity of command module. So we know that velocity is equal to distance divided by time, and the distance is calculated by 2 pi r, and the time it takes is the period. So we can sub in the radius and the period. So 2 pi times 1.85 times 10 to the power of 6 divided by 119. And this is a tricky part because we need to convert minute into second in order to finish this question. So we need to divide by 60 at the end. So we got the velocity is approximately 1628 meters per second. Let's conclude what we have learned today. Circular motion is an object traveling at a circular path, and a centripetal force is necessary to keep the object moving in a circular path because a centripetal acceleration is important to change the direction of the velocity. And these are the 3 very important equations for circular motion. Thanks for watching the video.